let's move on to the next the papers. The paper title is the Design for 3D Stacked Neural Network Circuit with Cyclic Analog Computing. So the paper will be presented by the Professor Kiyoyama. So I'd like to briefly introduce Professor Kiyoyama. Professor Koji Kiyoyama received the BE Master and PhD degree in engineering from Nagasaki Institute of Applied Science, Japan in 2000, 2002, and 2006. From 2007 to 2010, he was a member of research staff at the Microneural Machine Research and Education Center, Tokyo University Center, Japan. Since April 2010, he has been with the Department of Electronic Engineering, NIAS, where he is currently an associate professor. The Professor Kiyoyama's research is in the field of integrated circuit design, where he is interested in low power mixed signal circuit design, image data acquisition, circuit design techniques for three-dimensional stacked LSS systems, and biomedical applications. Okay, Kiyoyama-sensei, please.
Thank you, Professor Tanaka. Can you hear me?
Yes.
Okay.
Can hear you.
Thank you. I'm Koji Kiyoyama. I'd like to talk about design for 3D stacked neural network circuit with cyclic analog computing. This is the outline of my talk. First, I talk about the background of this work and explain our proposed 3D circuit. Then I'll move to the design of our 3D neural network circuit. Next, I'll show you simulation results. And lastly, I'll summarize my talk. Today, machine learning with accelerator chip. Okay. The chip for each types of data, such as images and sounds, have been expanding worldwide. However, accelerator chip or mobile products have heavy constraints on computing resource, power, and flexibility. As one solution, proposal for accelerator chips with analog computing are increasing. This figure shows different types of chip configuration. This configuration as an accelerator, such as FPGA, in which the processing element unit PE and memory are physically separated from each other, and this computation is often used. And this type is the technique for running computer calculation entirely in computer memory. For example, RAM, and is high efficiency without the need for data movement. And near memory computing also use standard memory, but to put processing unit very tightly close the memory. We propose a near memory computing neural network circuit using the 3D IC stacking technology. This slide shows analog computing for neural network circuit. In analog computation, the atypical neural model is usually replaced with a crossbar configuration. As you can see on the side, multiplication can be done with a resistive device that uses non-volatile memories or transistor. In this figure, the input activation X1, X2 are here voltages. The weight W1 and W2 are transconductance of the transistor, for instance. And by Hopf's law, these snaps are just multiplying current. So basically, crossbar is multiplying and adding the power. This slideshow gave an overview of analog Mac. A typical analog-based AI accelerator requires number of analog to digital converters, ADCs, and digital to analog converters, DACs. According to previous research, these ADCs and DACs for crossover configuration consumed about 18% of the power and power consumption and circuit area. We are aiming to develop a neural network circuit can compute both image and time series data, and we designed a proof of concept chip. The design circuit operates cyclic processing between neuron chips to reduce power consumption to ADCs. And the Mac circuit is designed with high linearity and low noise to raise the analog signal processing. Now I'd like to move to the next section. This slide shows a conceptual diagram of a proposed 3D stacked neural network circuit. Proposed 3D IC is a total of 4-layer stacked chip, consists of 2 neuron chips that mainly perform analog Mac operations, and 2 memory chips that store activations and weights data, with digital data. The chips of the neuron chip number 1 and 2 are same chip, and neuron chip 2 is face down, loaded, and then actually connected by neuron 1 by microbumps. This slide illustrates a simplified schematic and show connections between neuron chip 1 and neuron chip 2. Neuron chip 1 and 2 are connected face-to-face using microbump. The signal is after the weights and activation are written from memory chip to neuron chip by 8-bit resolution DACs. Cyclic operation performed between the neuron chips. After cyclic operation, the activation are converted by the 8-bit resolution ADCs at any timing and stored the memory. Next, I'd like to explain the circuit configuration. This circuit shows the input-output circuit from 1 neuron to 1 output neuron by 1 synapse. The input neuron is a sample hold circuit, and the synapse circuit uses the same circuit consists of a MOSFET capacitor for positive and capacitor and switch. So it's positive and negative. The output neuron is a programmable gain sample hold circuit used for output function. The output function fx, which can select bypass or sigmoidal and little function. This slide shows how to set the conductance. The conductance is set by gate voltage of MOSFET. These plots are IV curve of the NMOSFET. This schematic shows the connection of only neuron synapse and the other. The voltage source terminal is fixed by virtual short of the amplifier. by setting Vi to a constant voltage within this range, the drain source voltage VDS become a linear resistance so that the GDS with high linearity can be used. This slide shows a brief overview of our analog Mach method. Upper figure shows the voltage waveform of the voltage to time converter, and the middle figure shows the output current of synapse, and the lower figure shows the output voltage of the other. The time to voltage type conversion circuit use a comparator and a lamp wave to convert all the input voltage into a constant voltage and value with pulse. The voltage pulse multiplying by the conductance produce the current shown in figure. Finally, the current of the snaps connected to this one line accumulated by other and convert into voltage. Here, I talk about need for noise reduction technique. As we all know, in cyclic operation using analog signal, noise amplifier is accumulated. Their computation accuracy is degraded. For that reason, we designed the current adder using CDS technique to cancel the noise voltage. So our adder has two key features. First, calculation of the addition and subtraction with high linearity. Second, it's a reduce of the noise of amplifier. The design adder consists of one amplifier, one capacitor, and 5 switches. Next, I'll explain this adder. Let's look at the operation of an adder circuit. The adder has 3 operation phases: reset and noise charge, and positive current transmission, and negative current subtraction. First, during the reset and noise charge phase, the capacitor of the adder is reset. At the same time, the amplifier is connected to the non-inverting unity gain configuration to charge the capacitor with noise. Phase 2, adder accumulate the currents from the positive synapses. The output voltage at this phase is given by this equation. Finally, the operation is completed by subtracting the currents of the negative synapse. From these equations, we can see that the noise voltage of the amplifier, so Vn, is subtracted only the signal is output. Now I present the simulation results for the design analog Mach. This is the dye microphotograph of the neuron chip. Chip was fabricated in 0.18 micrometer CMOS, and chip size is 5 by 5 millimeter, and the designed neuron chip that integrates 64 neurons and 64 by 64 synaptic connections. Here are the voltage setting conditions. This slide shows the simulation results of our other circuit. Here I show simulation result which in current of 8 microampere flow in only one side of positive or negative synapse respectively. The upper waveforms are currents that have passed through switches, and lower one is the output voltage of other circuit. So this time is phase 1, and resets capacitor and store the voltage, the noise voltage with the amplifier. Next, the other accumulated current from the positive synapses. As shown in equation, when the constant current flows through the other, the output voltage becomes a proportional waveform. In the phase 3, so other capacitor switches connection between the top and bottom terminals. Therefore, output voltage rotated around VCM shown in figure. In phase 3, the negative current is 0, and this voltage is 0, and so that voltage doesn't change. This voltage is the result of multiply accumulate operation. And similarly, the following slide shows the simulation result when the positive current is 0. Here is the phase 1. Next, during this phase, the positive current is 0. So there is no change in the other. Phase 3, the final calculation. The other accumulated current from the negative synapses. The output is lower than VCM because it is a mark operation for negative synapse and only synapse and activation only. The current consumption per mark operation was 431 microampere with a 1 input to output circuit by 1 synapse. Here I show the result of the linearity. The positive and negative currents to the other drop to 8 microampere. From this result, it's confirmed that the linearity of the output voltage is 1.6 volt or more, which is a wide range. This slide shows the simulation result of connecting DC voltage, assuming an input of the voltage VOS to amplifier. To verify the VOS reduction, the output voltage was held at phase 3 in this simulation. From upper waveforms, DC voltage in the range of plus minus 8 mV is reduced to less than 0.1 mV by CDS. Finally, I'd like to conclude my presentation. We are aiming to develop the neural network circuit that can handle both image and time series data. From this purpose, we have designed a proof of concept chip. So we're currently evaluating the manufactured chips and will publish the measurement results soon. Thank you.
Okay, thank you, Professor Kiyoyama. So this paper is open for discussion. If you have any question, please use the chat window or raise your hand. Okay. Okay, Professor Kiyoyama, I have one question.
Yes.
So you mentioned about the cyclic computing may reduce the ADC powers. So my question is, how many percent of power will be reduced?
Okay. So this slide shows the memory chip. So dark power consumption of 63.3 milliwatt at 64 ADCs. So this power is reduced to cyclic operations. It's okay.
Okay, so how many percent of power reduced compared with the other systems or other?
So simulation results show that the power consumption of 64 input-output neuron chips is about 40 milliwatt.
Oh.
So yeah, and same that dark power consumption. So it's about 1%. Yeah, sorry. So
Okay.
63. So yeah.
Okay, so any other question from audience? Okay, I have one more question. So your system use the capacitance, okay?
Yes.
And I'd like to know the capacitance value and retention time, required retention time for capacitance to keep the capacitor value.
So in this design, capacitor will keep retention time.
Capacitance value and retention time to keep the charge.
Time charge. So it's keep time either up to 10 milliseconds at the resolution of 8-bit resolution. So capacitance is the 0.3 picofarad in this design. 0.3 picofarad.
Okay. Okay, thank you very much. So, is there any other question? Okay, the schedule is a little bit behind time. So I'd like to finish this. I can finish this presentation. Okay, thank you very much.
Thank you, Chairman.